Okay, so until the rest of the guys will be back, I'll just do a quick recap. We've started to study about subsequences and partial limits in order to say something meaningful about series that does not have sequences or that does not have a limit, like -1 to the n, which has the partial limit -1 and the partial limit 1. And we wish to speak about those. And one question that I asked, and could be asked in several different ways, is does there have to be a partial limit at all? Could there be a sequence with no type of converging behavior, meaning that there is no subsequence that converges to something? And the answer, there couldn't be such a case because of the theorem I quoted last time, but I didn't prove it. I will prove it today. For every sequence, there must be a monotonic subsequence. So you can choose the elements, infinite elements that are either going up or going down. One of the cases must be true. And the monotonic sequence is always has a limit. Either it's bounded, it's converging into a finite limit, or it's unbounded, and then it tends to infinity or minus infinity, depending upon the direction. So that's basically the answer, that every sequence must have a subsequence that has some limit. And one of the famous conclusions is called the Bolzano-Weierstrass. Now let me make sure how do you write Weierstrass. Weierstrass. Oh, I didn't guess it. So the Strass makes sense, but this. Okay. Weierstrass. Okay, so Bolzano-Weierstrass theorem says that every bounded sequence has a finite partial limit, and it's a direct result of this theorem, since it has a monotonic subsequence, and this subsequence is both bounded and monotonic, therefore converges to some finite limit. You will see later that this theorem is needed and helpful in proving some theorems about functions. Okay, so now let's prove that every sequence has a monotonic subsequence. And I'll remind you, last class, I urged you to think about the proof yourselves, and I've shown you it's not that trivial. And I promised you that the proof doesn't require calculus knowledge. You can explain it in layman's terms, and you will see it's a rather elegant proof. So define a peak element, like the peak of a mountain. Define the peak element to be an element A, K, such that for all n after K, it is true that an is smaller or equal to AK. So basically, in simple words, a peak element is an element that is taller, if we talked about the international students, than everyone behind him in the queue, right? So AK is larger or equal to all elements that comes after it in the sequence. Such an element will be called a peak element in the sequence. There doesn't have to be peak elements, but if there is one, that's its name. Yes. Yeah, that's what you wanted to ask?
No, I wanted to ask what you want to ask about.
First, we never talked. You see in the such a peak element you did speak about, I think, yeah. But what do you do with peak elements? That's the main point, and it's very elegant. If there are infinite peak elements, take A, K, N to be the subsequence made up of all peak elements. So if the sequence has an infinite number of peak elements, such peak elements, I'll take them to be the subsequence. This subsequence, what can you say about it? Is obviously
constant.
No, it's not constant. A peak element is larger or equal to everyone that comes next.
It's monotonic.
But what kind of monotonic?
Non-increasing.
Decreasing. Decreasing. Why? Because every monotonic. Because every element is bigger than whatever will comes next. So if I took all the peak elements, any of them is larger than all the rest, that is a decreasing subsequence. Agreed? So if there are infinite peak elements, there is a decreasing subsequence. Okay, so we're left only with the case that there is a finite amount of peak elements. Agreed? Otherwise, there are only a finite amount, there is only, sorry, there is only a finite amount of peak elements. And take the first element of the sequence after the last peak to be the first element of our subsequence. Called it AK1. So in simple terms, I chose an element of the sequence after the last peak. Since there are finite peaks, there is a finite amount of peaks. I can go to the last one, take one step forward, and this is the first element of the subsequence. Since AK1 is not a peak, it's not a peak of a mountain, it's not a peak element. What does it mean, not being a peak element?
Being a valley.
No.
That it's smaller than the subsequent.
Then who? A peak is someone who's bigger than all of the members who comes next. So if someone is not a peak, what is the reason? Yeah, because it's after the last peak, right? I took all the peak elements, and then I went one step forward. There are no peaks anymore, right? At this stage, say you have 50 peak elements. You go to the last one, the 50th. Afterwards, there are no more peaks because they're all at the start. Okay, if there was, it wasn't possible, there was an infinite amount of peaks, and then we have a decreasing monotone subsequence.
I missed the last.
Okay, yes?
So would this sequence, if you were to draw it on a graph, it would be like this.
Which, the peaks you mean?
Yeah.
But I ignore them, they are not my subsequence now, I ignore them. You will see what I'm-
halfway through writing it.
Yeah, no, I will see what happens, but I have a finite amount of picks, I ignore them all. And I skip ahead after the last one, and I take the first element after the last pick. It is not a pick because I skipped all the pick elements. What does it mean that it's not a pick? Again, a pick element is bigger than all the rest, all the following ones, so why am I not a pick?
There are bigger elements.
There is at least one element bigger than it, right? So there exists an element AK2 such that K2 is after K1. It's if we're thinking about the queue, that it's behind me in the queue. If I'm thinking about the sequence, then it's forward in the sequence. So there is an element afterwards, and it's bigger than the last element. Great, because it's not a peak. Some element go past it. Again, AK2 is not a peak. And we continue recursively and to build an infinite subsequence, which is increasing. Exactly. Like I said, quite elegant. Okay, either you have infinite peaks or finite amount of peaks, and if you have finite amount of peaks, every element who's not a peak have someone larger than him, someone taller than him afterwards, and then you can build an infinite sequence because there are no more peaks left. Okay, that's the ingenious thing about all of the thing, and I will say. Our discussion after next lesson, I just remember this morning, to be honest, that when I was a TA, I proved this theorem because I thought it was an extra sum. So when I did it myself, I did it like you suggested. If it was bounded, I took the supremum, and then I took elements that are closer to the supremum. It does work. I just remember that I did this, but that's a theorem from the class, and it has nicer proofs, and this is.
The other one is just more to.
Yeah, but this is elegant and easy and doesn't require the knowledge of supermoons and whatnot. In any case, so and that's that. Any questions up until now? Yes, Simon.
What is it that we were proving?
That every sequence has a monotonic subsequence. You remember, we talked about it last class, we just proved it, okay? Okay.
And we proved it not through the book, Boltzmann was
No, Boltzmann-Weierstrass is a conclusion of the theorem. And it's an easy one, I just told it, I mentioned it, Belpe. What do you say in English, Belpe? By heart? It doesn't-
Yeah, by heart.
Yeah, that's it's weird for me to say, but I mentioned it and didn't write it down, the proof of Boltzmann-Weierstrass, because it's so immediate. Because if a sequence is bounded, then by this theorem, which I did prove, it has a monotonic subsequence. This monotonic subsequence is both monotonic and bounded, therefore has a limit. That's the proof of Boltzmann-Weierstrass. And some students ask me, so why does it name after two people if it's so easy? There are many reasons for the name, but I'll just say that usual proof of Boltzano-Weierstrass is more complicated. This is a rather modern proof to it, which is nice. But there are in like at least in Israel, the way that it used to be taught for years by Meisler was without this trick. It was a more direct, interesting proof, but much more challenging and not necessary. Okay, and any questions so far? Okay. I will make a few claims without proofs, and then I'll mention another definition and a few claims. Some of them I will prove. Okay. I don't know. Just telling you in general. I don't wish to go too into subsequences. You can go very deep into it. By the way, that's a note, and Tomas, I'm appointing you to be on it. If the homeworks will go too into subsequences, then tell me before you break your head or your heart, because I'm planning not to go too deep into that subject. And the possibilities there to ask a very hard question is there. So with a maths major, usually that's what we do. So if you see the homeworks are too deep in this subject, then tell me, and I'll tell me that it's too much in my opinion, because I'm not going to too deep into it. Okay, so theorem without proof. If AN does not have an upper bound, then infinity is a partial limit of this sequence. Well, that's not very hard, but it's not the end of the theorem. Okay? If n does not have an upper bound, it's rather easy to build a subsequence that goes to infinity. And if AN does not tend and we should say also, it's not a different case. If also it does not have an upper, no, sorry, not also. And if AN does not tend minus infinity and has an upper bound, then it has a maximal partial limit, which we define to be lim sup of A. Sometimes it's written lim with an overline, right? And overline limits of A. Okay. It's easier for me to write lim sup, so that's why I use it. That's the way we actually pronounce it. But the way it's written down, it's usually like that, a lim with a bar above it. So it has a maximal partial limit. It couldn't be that the partial limits are keep rising and have no maximum value. The maximal value of the set of partial limits is by itself a partial limit. That's the theorem. Okay?
Maximum partial limit is
Of all the partial limits, it's the biggest one. Right? If you look at the sets of points, the sequence tend to, subsequences tend to, there is one which is the biggest. That's of course if n does not have an upper bound. Okay?
it has an upper.
If it has, sorry, if it has an upper bound and it's not tending to negative infinity. Okay? we define similarly the smallest, the minimal partial limit to be lim inf of n, which we write underline, under bar, of limit of n, that's the lim inf, and an tends to the limit L if and only if the lim sup of an is equal to the lim inf of an equals to L. For instance, example, I think it's an important one. Look at the sequence an, which is 1 over n. What would you say is the lim inf of this sequence? What is the minimal partial limit of 1 over n? 0. What would be the lim sup of an, the maximal partial limit?
Also 0?
Yes, Thomas, very good. But I hope some of you at least got confused, because if I just speak about the supremum or the infimum of the sequence, the infimum is 0 and the supremum is 1. But I'm not asking about the biggest element, about the supremum of the elements. I'm speaking about the infimum or the supremum of the partial limits. And the only partial limit of this sequence is 0. Why? That's exactly what I've written at this sentence. If the sequence, tends to L, then it's both the maximal partial limit and the minimal partial limit. So since this sequence tends to 0, it has a limit, so both the maximal partial limit and the minimal partial limit are equal to the limit. And if you have two different partial limits, like some of the elements tends to -1 and the others tends to 1, that it stands to reason, and it's true that the sequence itself does not have a limit, it does not converge at all. That's what we're saying here. Everything I said here is within your grasp, but like I said, you can dive into it, and I wish not to do it so deep. Yes.
Do you mind writing a counterexample, like as an equals sine n is a counterexample where
-1 to the power of n is the easiest counterexample.
Sure.
Because sine n is a hard counterexample, because it's very hard to prove about subsequences where they converge, because the values within the sine are radians, and you put natural values, so I'm not actually sure. I am sure, but it's rather, it requires harder tools to work with. But I will write -1 to the n, because that's the go-to example. Example, if an equals -1 to the power of n, then the lim inf of an is -1, and the lim sup of an is 1, and therefore an does not have a limit. neither finite nor infinite. Okay? And because the lim super lim inf are different than one. And any questions so far? Okay. And let's do one example, which is I think two, right? But one hard example, let's say. And assume there are infinite elements of an that are smaller than 1. Prove that lim int of an is smaller or equal to 1. First of all, does that make sense, the claim here? If I have infinite elements of the sequence that are smaller than 1, then the minimal partial limit must be smaller than 1. Yes? I didn't say that. Say infinite elements, not all of the elements. Right? Like the odd places or the even places or the prime number places, right? I'm saying there is an infinite number of elements, but not all of them. Not all of them. Okay? That's the main difference. We proved such a thing earlier on the semester, and I said if all elements are smaller than A, then the limit is smaller or equal to A, right? But here it's not all elements. That's why I decided to do this example, because it shows you the kind of things we can say about partial limits, and the kind of thing they allow us to say, right? Because I couldn't say anything about the limit because there might not be a limit to the sequence, but I definitely can say that the lim int is smaller than 1. And the reason I didn't skip it altogether is because you'll see later that some of the theorems, the most general case, can be phrased only using lim int, because sometimes what we wish to say we wish you to say about sequences without limits, but they always have a lim inf and a lim sup. You will see it in series when I'll get to it. Ratio test and root test. Okay, so that's what we need to prove. And the solution is quite easy. I'll let you try it. It shouldn't be. It's mostly words, like it says, and we do use the theorem, right? But we don't need epsilon or anything like that. Do you have any suggestion as to the first step? How can we start? Yes.
Well, first we need to build a subsequence
Of what?
of elements that are below 1.
Exactly. Okay. Look at the subsequence A, K, N of all elements of the original sequence that are smaller than 1. Since there is an infinite amount of such elements, you can build a subsequence. If there was only a finite amount, then it's not considered a subsequence, right? I couldn't take like 3 elements and say that's a subsequence. No, but we've said it's infinite. I'll write it. This is allowed since there are infinite there is an infinite amount of such elements. Okay. Next,
We break it into cases or that's the.
no, just by the theorems, we don't need anything.
We need to first. Move the limit of that sequence left of one.
But the subsequence doesn't have to be converging. That's the problem, right?
Oh, but
There could be balagan under one, right? Some of the elements could go to -2 and some of the elements could go to minus infinity or -3, right? Yes, but it doesn't have a limit.
But it has a
A lim sup by itself. Yeah, okay, so now I can look at the lim inf of this sequence. It's a bit weird for me, but it's true. I will use the theorem. Take a monotonic subsequence A, K, M, N. Take a subsequence of the subsequence, which is a sub
Oh, no.
subsequence of the original sequence. But saying subsequence is a bit of a joke
don't show.
because it's subsequence, therefore subsequence. Right? Because it's still these are still elements of the original sequence, whatever. But because it's monotonic, then A, K, M, N tends to L, which is smaller or equal to 1. L is a partial limit of AN, and therefore bigger or equal to the least partial limit, which is lim inf. So we get finally that the lim inf of AN is, sorry, I wrote -1, right? And the limit of AN is smaller or equal to 1. So what I did in few quick words, I took all of the elements below 1. It has some partial limit, and this partial limit is below 1, and the lim inf is the smallest partial limit. So it must be smaller than L, which is smaller than 1. Sorry, yes, that's what I meant to write.
Did we prove that the monotonic sequence has a limit?
Yes, we've proven that that's the main theorem about monotonic sequence, which I made a whole fuss about and told you solve from the exam and whatnot. And the theorem says that either it's bounded and it has a finite limit, or it's unbounded and it has an infinite limit. So L might be negative infinity, but then still the lim inf is negative infinity, which is, this is not the most exact way to talk about it, but lesser than 1, let's just say. And so this is kind of like where we could go to with these kind of questions, and I will not do it too much. I will not go any further into that direction. Okay, any questions up until now? Yes, sir.
I'm just struggling on something very last time. No, the words of the. That's a possibility of there. Like
Yeah.
that.
Yeah, because we found a subsequence that goes to L. So it's a partial limit of the original sequence. You found some elements that goes to this number. Give yourself in your head some number. Say L is -2. So you found elements from the sequence AN that tends to -2. Do you agree? That makes it a partial limit. And the lim in, by definition, a partial limit is a point in the line of numbers where there is a subsequence converging to. And the lim int is the smallest, is the minimum of all partial limits. So if you found some partial limit, the limit is even smaller or equal to that. And that limit must be below 1 because you took only elements below 1, and that we proved. If all elements of a series are below 1, the limit is smaller or equal to 1. That's we've proven. The main trick was to take a converging subsequence. Okay? And because we first had to take the subsequence of elements smaller than 1, like you, Sammy, yourself said, then we have to take a converging subsequence. Right? First of all, I took only, like if we talked about the Q of international students, right? And I told you, find a sub Q which is monotonic in height. Could you find a sub Q of international of international students of the same gender and monotonic by height? A real question, okay? You have an infinite queue of international students. I want a sub queue which consists only of students of the same gender and monotonic by height. Is that possible? What do you say?
But it's in theory, yeah,
How? But how? How do I do it?
take all the geeks that are male or are female.
That's it. I find that there are either infinite number of males or infinite number of females. Okay. And then you take the subsequence of male or female, and then you take its subsequence, monotonic subsequence. Exactly. So it's kind of like what I did here. That's what I meant. Sometimes I wish to go into a subsequence of just elements that I wish to study, and then a subsequence to make sure it converges. Either converges to a finite limit or goes to infinity or minus infinity. Any questions so far? Okay. So the next and final, sorry, subject in the sequences will be Cauchy sequences. And again, I will go through it rather quickly, but I don't wish to skip it all together. I think it's important. So what are Cauchy sequences? Like always, I will start with an introduction and a question. Suppose the difference between every two adjacent elements tends to 0. Does that mean that AN must converge to a finite limit? What I'm trying to get at, the idea of Cauchy sequence, before I will answer the question, the idea is to be able to speak about converging sequences without mentioning their limits. Why would one want to do this? This is one way to, this is one of the ways to define the real numbers using the rational numbers, because we can't speak about the square root of 2 because it's not a rational number, but I can take a sequence that's supposed to converge to square root of 2 without actually speaking about the square root of 2. Okay? And there, sorry. So again, instead of talking about the limits, I wish to talk about how close the elements are to one another. I'll write that as well. Instead of talking about the limits, we talk about how close are the elements of the sequence to one another. Okay, so that's the idea. If you have any question, now is the time. That's the idea behind the subject of Cauchy sequences. Instead of talking about their limits, we wish to talk about how close are the elements of the sequence to one another, and somehow know if the limit converge. So again, I'm getting back to my question. If an plus 1 minus n goes to 0, does that mean that an converges to a finite limit? Now I'm asking. Why not? Can you give me a counter?
Yes.
And now no. That's it's a theorem that is true for its hour. It was proved 5 minutes ago now. No, I'm not so sure.
I mean, does it have to converge something?
That's the question.
No, I mean, not finite, I mean, any.
Fine. By the way, the answer is similar, so you can take it the way you want it, but I mean a finite limit. That's the. So at first glance, it seems that the answer would be yes, because the elements are close to each other, but it's actually the answer is no. It could go to infinity, that would be the case I will show you because it's so easy, but it could also diverge completely. The sequence itself would go between negative infinity and infinity, all the partial limits if I would so wish. You have an example?
No, it's all that.
Okay, so example, say take an to be 1 over, not 1 over, sorry, be the square root of n, where obviously the sequence tends to infinity. Agreed? However, an plus 1 minus an equals the square root of n plus 1 minus the square root of n. How can you calculate this limit? How do you find the limit of that sequence? Right, it's a problematic case because it's infinity minus infinity, right? How do you solve it? We multiply and divide by the adjacent, yes. So it we multiply and divide by the sum of these two expressions. That's a trick, but it's a known trick. And we get n plus 1 minus n over sum, which is 1 over the sum, which is 1 over infinity, which goes to 0, yes. So here, the difference between any two adjacent elements tends to 0, and yet the sequence itself is somehow able to reach infinity. It doesn't actually reach it, obviously, but it tends to infinity. Another example, say A1 is 1, and say that the next element is always the formal 1 plus 1 over n plus 1. What does that mean? So A1, like I said, is 1. And the second element
It's not similar to the Newton graphs method.
is what?
Similar to the Newton graphs method.
Because they add something, I'm not sure
No,
why.
because the top one is the derivative of the bottom one, and that's equal to the current one.
I'm not sure, to be honest. So each element is the sum of the former element plus the last fraction. So A3, what would A3 be? It's 1 plus half plus a third, right? Where do you suppose this series tend to? Because look, an plus 1 minus an is 1 over n plus 1, and where does it tend to? 0. Agreed? But where does the sequence tend to?
E or something.
No, so it was if it was a factorial here. And plus 1. We have 1 plus 1 plus, yeah. But it's not in any case. And we will see, we will learn that an tends to infinity, actually. It's the harmonic series. That's we're almost at the subject of series, and series are the infinite sum of numbers, and that tends to the infinite sum of 1 over n. That's called the harmonic series, and we will prove that it tends to infinity, but that's much harder than this example, which was rather easy. But you need to get comfortable with the idea that the differences are goes to 0, but still they add up into a rather big thing, right? We take elements that their size tends to 0, yet their sum tends to infinity. That could happen. That's basically the main point about the next subject, which is series. Any questions up until now? Okay. So what are Cauchy sequences? So in order to grasp the concept of the elements and crowding together, we need to work harder than just the difference between two adjacent elements. And I mostly say it in order for me to give you the following definitions, in order for you to accept it. Definition. And we call an a Cauchy sequence if for every distance for every positive epsilon, there exists an index K such that for every two elements M and N after K, not just adjacent elements, every two elements after K, it is true that the distance between AM and AN not tends to, when I start with epsilon, I cannot finish with tends to, right? For every area, value, distance epsilon, from some point forward, the distance between any two elements, adjacent or billions of light years away, I'm not sure light year is actually an index distance, but whatever, it's smaller than epsilon. That means that they are crowded together. That you can bunch all of what is rest within an area of an epsilon, two epsilon to be honest, one epsilon near to the right, but the fresh thing here is that you can see that the limit is not mentioned. I'm not saying that they are close to a certain point of the real line. I'm saying that they are close to each other, but I do have to do it in this fashion rather than the easy fashion above using limits, because the easy fashion is false. This fashion is true. And the theorem without proof, and you can do it as an exercise if you like. In the real numbers, a sequence converges to a finite limit if and only if it is a Cauchy sequence. Just note, look at the following sequence. 1 and 1.4. Let's do the 3, 3.1, 3.14, 3.141. And just remember the next one, 3.1415, right? This limit, this sequence, sorry. In the real numbers, the real number field, which number, what is the limit of AN? Pi. In the rational numbers, AN does not converge since pi does not exist. But in any case, AN is Cauchy, right? Because all of the numbers here are rational numbers. So it is a rational sequence of numbers, and they are close to each other, right? Why they are close? Because within the real numbers, they have a finite limit, and from that, it's easy to say that they are close to each other because they are all within the area of pi, which is a small area, and they can't go too far from one another. But it is not considered converging because the definition of limit could not hold because the number is not there. I cannot say that there exists a number L that the sequence converges to because the number pi is not a rational number. So again, it's all about justifying why did we actually need to go to the real number field, because in the rational numbers field, calculus does not work very well. And just for general knowledge, and that's one of the way to actually define the real number field. You take Cauchy sequences of rational numbers, and every Cauchy sequence represents a number. Like this sequence would be the representative of pi. Okay, and every real number will have such at least one such sequence that represents. Yes.
I don't understand how this can be true for sequences that don't become constant at some point.
Because it gets closer and closer, but never reaches the point.
Because
Because you can go as close as you wish to any number with rational numbers. You can, and that example literally shows you how. Just add more digits, right? So if the pi number is whole, it's an integer number, then yeah, from some point forward it would be constant. But if the number has an infinite, it doesn't even have to be rational. Think about third, right? So you get 0, 0.3, 0.33, and so forth until infinity, and it tends to 3. It could be constant sometimes, but
can you go to the definition 1 second? To the definition
of Cauchy?
Yeah.
Yeah. It means that the elements of the sequence are close to one another, but not equal to 0.
Yeah. No, my question is because it's for any epsilon.
Yes.
Over
But for any epsilon, there is an index. So
a different index.
yes,
Okay.
yes, different index. Yeah, it's not from the same index always. So every size of error you wish, as small as you like, from some point forward it would work. The elements will be really, really close to one another. Okay? But for every size of error, it would be a different index. Just like the definition of limit. The main difference is that I'm not mentioning the limit here. I'm not saying a n minus l is smaller than epsilon, but I'm saying the difference between any two elements is different than epsilon. And it appears to be true. I will just say by heart the idea behind the proof. If the limit is sequence, it's quite easy to show which it is Cauchy. I told you this before, because all of the elements are within the area of the limit. But why? Because it's Cauchy, it must have a limit. It has to do with the partial limits before. If it had two different partial limits, then there will be a subsequence tending to this partial limit, and there will be a subsequent sequence that tends to this partial limit, and the distance between these two will be big and not smaller than epsilon, and you'll get a contradiction. So this is where I'm showing you the promised land, but I'm not taking you all the way to it. Okay, and you forgive me, of course. Okay, so that is enough with sequences. And so the story of the course, we have 4 chapters. I will call your computer science, so you will accept it. I will call the first one the 0 chapter. These will be numbers and boundaries, like supremum, infimum, and whatnot. That's just a warm-up for limits. The second chapter are sequences and limits. That's most of what we did in the course so far. I told you why. This is even due to Euclid. This is the basic of calculus and understanding the concept of limits. And the next 2 chapters are series.
SCRIE.
Oh, thank you. Series, infinite sums, which are more. They could even be a subchapter of sequences, but they are not. But it will be more of sequences and limit in a way. And lastly, it's the reason for the parting basically is functions. That's the main thing about calculus. We reach it by the end of this course. But like I said, after we've done our work correctly up until now, then studying functions will not be that hard. And so you are here. You are here. Okay. Any questions before I begin? Yes, Sally.
Just go.
The idea behind saying that the sequence is Cauchy means that the elements of the sequence are close to one another. Yes. I've claimed that he proved that it's within the real number field, it is equivalent saying that the sequence has a limit, that it converges. So saying all the limits are close to 3 is it says that the elements must be close to each other. And if the elements are close to each other, then they must be close to some point on the real line. That's what we're saying. And actually defining close to each other, it's not that easy. I'm saying by every distance I want, I wish from some point forward, the distance between every two elements is smaller than that given distance. And it basically means that it has some finite limit. I'm not sure which, because I'm just saying the numbers are close to each other. They all could be at the area of 3 or at the area of pi. Okay, it's my ability to speak about the converging sequence without talking about the limit.
Right, so
And sometimes it helps, not just when building the real numbers. Sometimes in series, I will show that the sum exists, but I'm not sure what is the sum. Just because the elements of the series will be close to one another, basically. That we will see. But for now, Cauchy sequence mainly says that the numbers in the sequence are close to one another. Okay? As you can see by the last inequation here. AN and AN are any two elements, and I say the distance between them is small. Okay. So series. And let's just start with the headline series. And let's start with a few examples. The example I like, and I will do it, I usually do it these days. Say you flip a coin until you get a tail and count the number of flips. Okay? What is the average number of flips? So, the regular one, right? It's not like the geometric harmonical one, no. It's a regular average. It's again a concept from probability.
It's
Okay.
Is it going to be 63%?
No.
I mean, it's really 50-50, but like it's
No, but I'm asking what is the average number of flips?
so Two,
How many flips?
is it two or something?
Maybe. So what do we need to do? So what is the chance we'll we will multiply each number of flips by the probability it will occur. Agreed? Makes sense? Right? So what are the chances for one flip?
One,
Half, right? The probability half. The first flip comes out tails. What? What do you mean always? A coin, a balanced coin.
Every number of flips. It's-
No, it couldn't be. It couldn't
No,
be.
but when you count two flips, you say that the first flip is the head, it's like this, so you only.
So that for two flips, the first flip must be head,
So
and the
it's
second one must be tails. So it's a quarter, it's half squared. Right, it couldn't be that you have more than two options with the probability half, right? Saying this, this juice is half apple, half banana, and half orange. That couldn't happen, right? So it's a quarter, yes, it's a quarter times two,
why two?
that's two flips.
No, but there was no.
The probability for doing exactly two flips is a quarter, because it's the probability of going heads at the first flip and tails at the second flip.
I'm not convinced. I thought it was 1/2 times 1/2 and not two.
Yeah, no, that's the probability. 1/2 times 1/2 is the probability. But I multiply the probability by the number of flips because I'm looking for the average of number of flips. Okay? What is the probability to get 3 flips? 1/8, because they're going heads, tails. Okay,
So it's
and so forth. Until infinity. That's the main point. Because this is not your course about probability, you will have one. But you see, I like to give you an example as to why do we study these subjects. Every subject has some needs, some reason to learn it. So theory have many reasons to learn it, but one of them comes from probability. This so-called simple example require you to understand infinite sums. I need to understand what is this infinite sum as to find the average probability. Agreed so far? Okay, so in probability course, you will define, it won't be even called an average, it will be called תוחלת. It's mean, תוחלת is mean? Could be, I'm not sure. In Hebrew, it's the ממוצע ותוחלת. Whatever, you'll get some definition for it and you will study it, you will be delighted. For now, I'm just saying this kind of makes sense. And you see that even for this easy example, since there are infinite number of options, results to the so-called experiment or game, you need to be able to sum them all up in order to do an average. And you need series for that. You need that language to be able to calculate them. Any questions so far? Okay. So now, as a further look into the future, I will calculate that infinite sum, obviously using tools we don't understand as of yet. It's a bit funny because it usually convinces, it will convince, you will be convinced that it's true. You won't even know what the problem is with what I'm doing, but during calculus 2, you will learn why what I did is a problem and why is it not a problem, because it works. But again, I wish to show you where are we going with all that, and what I will show you, it's a lot of calculus 2 as well. Calculus 2 deals with sequences and series of functions, and I will use that. And what can we do with them? So hold on to your seats. First, write the sum. It's the sum from n equals 1 to infinity of 1 over 2 to the power of n times n. Do you agree that is the sum here?
Yeah.
Okay. Next, we will look at the function f of x, which is a series of functions, which is n times x to the n. I like to put a spotlight here on the fact that we've made things worse. Sometimes in mathematics, you need to take a step back in order to gain momentum. So this is a specific case of this general case, right? So f of half is what we are interested in. Do you agree? Okay, so instead of doing just for half, I'm doing it for general x. It seems harder, but it actually helps. Remember, I will prove it later. The sum of the infinite sum of a geometric sequence. When I'm saying remember, in Israeli high school, you learn it in 5 yechidot. I'm not sure any of you learned it. But in any case, I will prove it, but for now, I just need the formula. The sum from n equals 0, sum from n equals 0 to infinity of x to the n is 1 over 1 minus x. Okay. Again, if you don't know this formula, I will prove it. It's actually quite important. For now, I'm just mentioning it. Okay. And now I wish for your help. Why? I know this sum and how to calculate it. I need this sum. What is the difference between this and that?
It's multiplied by
The n, right? How can we do something to this series right here? Differentiation, exactly. You cannot multiply by n, and I will show you why. Look at the elements here, actually. It starts with x, and then 2x squared, and then 3x cubed, and so forth. Agreed?
Yeah.
It's not the same n, right? You cannot just multiply each element by the, but you can derive this, and you get almost that, right? Not exactly, but almost. And why are we allowed to derive the way that we do? That's like 2/3 of calculus 2. Okay, but let's just do it quickly. So derivatives of 1 over 1 minus x equals the sum from minus n equals 1 to infinity of n times x in the power of n minus 1, which is 1 plus 2x plus 3x squared and so forth. And why do we start here from 1? Because the derivative of 1 is 0. Okay, it's the little. I'll derive the function, it's 1 over 1 minus x squared. That's equals that. We're almost there. What should be the last step to get here?
What about the minus?
And internal derivative.
Multiplied by x.
We multiply by x, and that is allowed because it's the same x. It's not the index of the sum. And so x over 1 minus x squared equals the sum from n goes to 1 to infinity of n x to the n, which is x plus 2x squared plus 3x cubed, so forth, like we wanted. So, and the average is, like we said, f of half, which is half over 1 minus half squared, which is actually 2, like Thomas said, but I'm not certainly convinced he went all the way to get to 2 this way. But yes, the answer is 2. On average, you will make 2 flips, apparently. Any question? Yes. Seems so easy. How did we not have
Questions is into
Intuitive, yes,
Yes.
yes. No, you're right. So the main, I think the main intuitive thing here is this step. Why am I allowed to derive this way? Why the derivatives of the sum is the sum of the derivatives. And that we will, like I said, we'll answer in intuitive. Other than that, it is intuitive one, but we didn't study it yet, is this series, infinite sum. We wish to learn about it. I've just shown you an example as to why it's important. Like probability, it's not the only reason, but it's some of them, one of them. Let's just go another example from the future, and then I will go to, I continue. Say f of x equals sum from n equals 0 to infinity of x to the n over n factorial. It's for you, Thomas.
Is it 2?
No, okay, it's not for you anymore. And you're closer. So that's the series I'm looking at now. Okay. What is the derivative of this function? Skip the sum, the summation sign. Just move to the polynomial notation. What is the derivative of this? What is the derivative of 1?
0.
Plus, what is the derivative of x?
1.
What is the derivative of x squared over x?
over two.
It's x.
X,
right?
Yeah.
What's the derivative of x cubed over 3 factorial?
3
X cubed over 2 factorial, right? That's x3 over 3 factorial.
It's just the same thing.
Yeah, so f of x equals f tag of x, and f of 0 equals 1, and one can prove that f of x must equal e to the x. So I'm not going too much into it, also to save something for the calculus 2 teacher to make you happy about, but yes, it's Taylor, McLaurin, whatever, yes, exactly. That is the main, we study sequences of functions mainly for Taylor. The other one, by the way, was also Maclaurin. This is also Maclaurin, And this is also Maclaurin, these are all Maclaurin.
But yeah, one over one minus x equals one plus x squared, where did that come from?
This?
We just did that.
This or this,
The top line.
this,
One over one minus x equals one plus x squared, did you just say
wait,
that?
this,
Not that. On the right. It equals-
no,
one plus x
this,
plus
this
Did
is
you just
this,
say that?
no, this is that. I just put in ends,
Oh, right.
Yeah. I'll put it here, okay? That wasn't the surprising bit.
Wait.
This equation is the surprising bit, right? But this is just, I like to write it as a polynomial, okay? An infinite polynomial. So yeah, these are Taylor sequences, the series, that's exactly that, or Maclaurin, around 0. So yeah, it's that. And okay, so now that we established dominance, we established that series are important. Let's start boring. Let's start studying that. It will still be an introduction. I will do introduction, I think, until the end of the class. But again, important introduction. What is the sum -1 plus 1 minus 1 plus 1 to infinity? Okay. Warning,
Trigger warning.
number 5 did it
Oh, that's why.
wrong. Yes, it's the most famous video about the number of 1 plus 2 of the whole integer set being equal to -1 over 1/12. So the result does have to.
They said at the very end that.
That's what?
They said at the very end that it's because you're dealing with infinity and so it goes weird.
No, they're claiming wrong stuff in the video. I hate it. Because for years after, it took some time, the wave started hitting me. And the first time I didn't know it. Some student told me, why is -1 over 12? I said, it is not. And then I understand in what kind of sense it is, but it's not the sense that we do in this class. And the way that they explain it in the video is plain lies. Okay, but other than that, what is this sum? So look at it, and you'll see why it's so confusing. On the one hand, we might say it is -1 plus 1 plus -1 plus 1, so forth, which obviously equals to what? 0. And we also might say it's -1 on the other hand, sorry. On the other hand, we have -1 plus 1 minus 1 plus 1 minus 1, so forth, which is -1. On the third hand, we can reorder the elements and say that it's -1 plus 1 plus 1. That is 1, right? Plus -1 plus 1 plus -1 plus 1 and so forth. Since you have infinite numbers of 1s and -1, you could just imagine you took just one and brought it
And then
to the
it's
front,
over
and
12.
that equals one, right? And you can see that I can pretty much make it any integer number this way, right? So that's a bit confusing. Also, yes,
Minus 1/12.
on the left leg, and one might say that minus one plus one, so forth, is equal to the limit when x tends to minus one of one plus x squared plus x cubed and so forth. Yes, no, but does that make sense? Because if you plug in minus one to the right, you get one, minus one, plus one, minus one, and so forth. Which is, like I said before, the limit of x equals to minus one of one over one minus x. And what is that limit? A half.
That seems more believable.
That's actually what number files is saying, but what they say, you're welcome to watch the video because I was shocked. I watched it a few times. It said it showed that it showed why would it be zero. It showed why it may be one. Say let's take a number in between, half. That's that reasoning for why they took half here.
Let's see the comment section.
Yeah. And but that's a more mathematical approach as to why you get to half. It's one way to go about it. So what was the point of all the limbs here? What was the point of all these limbs? We can define infinite sums in many ways. We will choose one definition to work with, and with that definition, the sum of the integer number would be infinity and not negative 1/12. But we will choose one definition, and it's not at all obvious it's the right one, because everything I said made some sense, right? But our definition will have to be one, like we do in mathematics. The actual answer is that this sum does not converge. It does not have the series does not converge. You will see it according to this definition. But according to other definitions, it may be, half. So, and next time we'll start by defining an infinite sum, a series, and then we continue. We'll move forward. That's it for today. Have a nice day.